I'm a PhD student at Swansea University, and I'm going to talk to you today about some work I've been doing using persistent homology to do quantitative analysis of phase transitions in two-dimensional XY models. This is joint with my supervisors, Jeff Gianser and Biagio. Okay, so you're probably asking, what is persistent homology? So this is a tool from the field of topological data analysis, which is sort of a maths field. And the tool was sort of developed in its modern form in the early 2000s. And since then, it's been applied to numerous different sort of scientific domains where it's seen fantastic success. And it's a way to sort of quantitatively summarize topological and structural features of data. People like to say it quantifies shape. But effectively, what we end up doing is sort of applying some algebraic topology tools to track things like connected components and holes in our data, basically by doing some linear algebra. So the general pipeline looks something like this. We take some data of some format, then we construct what's known as a filtration, which is a sequence of geometric complexes, which in some way capture the essential features of our data. And then we turn that into a persistence barcode, which tracks these connected components and holes through this sequence. I think it's easiest if we look at an example. And so this is a nice picture. So here, let's consider some data which is given by sort of a cloud of points in 2 dimensions. So you can see the underlying points here. And the filtration we're going to apply is called the Vittoris-Rips filtration. And the idea is that we're going to build up simplicial complexes on these data points. So a simplicial complex is made up of points, lines, triangles, tetrahedrons, so on. And the way we'll do it is we'll introduce more and more lines, triangles, and tetrahedrons at later and later values of the filtration parameter. I think we called it epsilon here. And so that we'll go from initially just the points to this big connected lump at the end. And we'll add in an edge. That filtration parameter equals to the length of that edge. And then if we have 3 points all connected to one another by edges, we're going to fill it in with a triangle. If we have 4 points all connected in by edges, we're going to fill it in with a tetrahedron. So that's our filtration, and there's a nice sort of illustration of certain points of it along the top here. And then we can track those features. So for example, if we want to look at connected components, that's called the zero homology. And so when we're just got the original points not connected at all, we're obviously going to have a connected component for each point, a whole load of features. But as we start connecting them up, we're going to lose some of these connected components, and we'll see that some of these sort of bars representing features here are going to get cut off until eventually we've just got one representing the whole sort of big connected component, which then persists on forever. We can do the same thing with the number of sort of one-dimensional holes tracked by the first homology. We see that in this first picture, there are none. And then in this second picture, we've got sort of, I guess, sort of 3 holes, but one has been filled in by a triangle already. So what we see actually is just 2 bars. And then if we look at an individual bar, so this top one, we'll see that it persists on in the next step. And indeed, both holes are still here. But by the next step, it should have gone. And indeed, we see that where this green tetrahedron has been filled in is where the hole used to be. And similarly with the other bar. And we can do this with higher dimensions too. H2 tracks a number of 2-dimensional holes. These are sort of enclosed voids. But realistically, we're going to mostly focus on looking at the 1-dimensional holes, first homology. Okay, so how does this, I should actually say, instead of just barcodes, we'll also look at persistence diagrams. The idea is that for each interval in our barcode, we're going to represent it as a point in the diagram. This is just another way to visualize this information. So given the left endpoint is the birth of the feature, and the right endpoint is the death of the feature, we plot it on the graph at point BD. And a nice thing about persistent homology is that for many choices of this filtration, the sequence of complexes, this resulting diagram is stable with respect to small changes to the input data. That is, with a sort of suitable choice of metric, a small change in your input data leads to a small change in this resulting diagram, which just makes this useful for sort of noisy real-world data, such as the type we look at. How does this fit into statistical physics? Well, I like to think that there are two paradigms, really. The first I call persistent homology of configuration space. And so this is about trying to analyze the topology of the space of configurations. So we could look at energy sublevel sets, for instance, and look for a sort of a marked change in the topology as we increase the energy. And this is the approach taken by Irene Donato and others in their paper from a few years ago. But this approach, it faces problems purely because the space of configurations is just that large. On the other hand, what I want to talk about is persistent homology as an observable, where we're going to take a single configuration and compute persistence in some way in order to reduce the degrees of freedom and capture the important features in those configurations. And this is the approach that's seen a lot of attention recently, with a lot of papers coming out over the last couple of years. And why might we want to do this? Well, the most convincing argument I think I can give is that of topological defects. So we know that many phase transitions are driven by or involve these topological defects, and there's a whole range of different ones. We want to be able to detect these in some robust way. So in particular, the models I've been looking at will have vortices and anti-vortices. They'll have domain walls, and they'll have these sort of half vortices on the ends of the domain walls. And so how we're going to capture these defects, well, that's where our filtration comes in. So as a setting, we take sort of the two-dimensional XY model. So an example configuration, it's like this picture here, got a 2D square lattice, and each lattice site we have basically an angle, or we can think of this as a unit length vector. And then the idea for our filtration is to sort of construct increasing subcomplexes of a filled-in version of this lattice. That's what this picture here is supposed to represent. And the idea is that we're going to start off with just the lattice sites, so the red points. And we're going to start adding in edges for filtration parameter equal to the difference in the spins on either side of the edge. So whereas in that example, we're looking at the sort of length of the edge, here they're all going to be the same. But what we care about is the difference in the spins on the other side. And similarly, we're going to add in a plaquette filtration parameter equal to the difference, the maximum difference between any two spins in that plaquette. And what we'll find is that we'll encode the defects I mentioned on the previous slide as one-dimensional holes. So we're going to capture that in the first homology. But with this framework, we could see how, higher dimensional defects might require higher dimensional homology. And one of the nice things about this filtration is it's very easy to show that stability property, where a small change in the spins leads to a small change in the resulting persistence. So as an example, let's look at a small configuration with an anti-vortex at the center. And then we've got the same idea here going from left to right. We're filling in more and more filtration. So on the far left-hand side, we're just going to have the lattice points, but I've just sort of got the more interesting section here. And we see that as we move to the right, we start connecting up more and more disparate spins. And we very quickly connect the spins around the outside of the lattice, which sort of varies slowly. And it very quickly makes this hole around this anti-vortex at the center, which only gets filled in right at the end because we've got these essentially 90-degree twists going around the central plaquette. And so what we see is this long persisting bar representing this long persisting hole. So the long bars representing our anti-vortex. We also get these short bars born early, which are representing these slowly varying spins, the spin waves. So what does this look like for real data? Well, we looked at the classical two-dimensional XY model, the Hamiltonian given here, spins want to align with one another. And we know that this has a BKT transition, temperature equals about 0.89, driven by the unbinding of vortex-anti-vortex pairs. And now I should mention the representation I've got here is what's known as the persistence image. And essentially the idea is it's kind of a density plot for how many bars we have of a given birth on the x-axis and length, persistence on the y-axis. So at low temperatures, we see that we have lots of bars which are born early and which are very short. These are the spin waves. But as we increase in temperature, we get longer and longer bars until finally we get this bright spot, finally, of the long bars that are born early and last throughout the whole filtration, our vortex-anti-vortex pairs. And then there's a phase transition somewhere between these two rows, and we see this marked change in behavior. And in fact, what we see is that this sort of spot telling us about our vortices and anti-vortices starts changing in behavior, sort of moving down this diagonal, getting born later and later. And moreover, we saw just general bars in our barcode are going to be born later, indicating the disorder. We also looked at what I like to call the ConstraintedXY model. That's an interesting one. So instead of temperature, our sort of parameter here is delta. And at a given choice of delta, we say that any configuration which satisfies the constraint that no two neighboring spins differ by more than delta is equally likely to be seen. Or equivalently, any constraint which violates this condition is not going to be seen at all. And this turns out to have a BKT transition as well, because we increase delta. But it's interesting to note that we've got this kind of cutoff effect happening. So in particular, we can't have any vortices for delta less than 0.25. We just sort of don't have the room to get around the circle. But it's interesting to note that what we get is a very similar looking picture to the previous slide, except now we've got this sort of truncated edge at the value that delta is. And then the other model we looked at, I call a PneumaticXY model. Effectively, we take the Hamiltonian we had for the classical XY model, we're going to add in an additional pneumatic term. That is a term with an extra factor of 2 in the inside. And so what this term does is it sort of doesn't care so much about the, well, it only cares about the axis of the spins. It wants the axes of the spins to align with one another. Or equivalently, we can think of the spins instead of being arrows as being sort of headless rods. And in our case, we set this delta trade-off parameter to 0.15. So really this pneumatic term is dominating. And in this case, we see two phase transitions as we increase temperature. The first is a magnetic pneumatic transition, which is second order in the icing class. And then later on, we see a pneumatic paramagnetic BKT transition as before. So in this first transition, what we're seeing is vortices stretching out into domain walls. That's what this picture up here is. So whereas before the vortex center was just sort of single plaquette, now it stretches out over a whole wall. And then the second transition is, well, these sort of stretched out vortices still remain bound with their stretched out anti-vortices. And in the second transition, these are allowed to unbind. We actually use two filtrations here. So this top left image shows the filtration I've been talking about, which looks very different. But then we also used a filtration where instead of adding in an edge at filtration parameter equal to the difference in the spins, we add an edge at filtration value equal to the sort of pneumatic difference in the spins, sort of the minimum angle required to align the axes of the spins. And we see a very familiar picture here of the BKT transition, which is fascinating because this is a sort of slightly different filtration. On the other hand, we see a very different picture for the icing transition. And in fact, it sort of happens up in this top right corner. What we instead see is the emergence of a cluster in the bottom right. So these are sort of bars in our archive that are born very late and sort of die almost immediately after. And that's showing us the presence of the domain walls. We can imagine that an edge crossing the domain wall only gets added to the filtration very late, because the spins are sort of pointing in opposite directions. So we might form a loop very late on. Then the corresponding briquette will get added in straight after. So that's these very short bars but born late. Okay, so that's nice and qualitative. The title of the talk is Quantitative. So how do we analyze these? Well, now we've got a familiar picture to some of the stuff we've seen so far. We're going to use some machine learning. In particular, we're going to train a binary classifier on these persistence images to try and learn the phases and produce sort of a phase indicator. We use logistic regression and k-nearest neighbors. And then we sort of train on low temperature persistence images and say this is the low temperature phase. We train on high temperature persistence images and say this is the high temperature phase. And then using histogram reweighting, we extract sort of a curve across the middle to obtain our sort of phase indicator. And then we repeat this for several different lattice sizes and try and look for some finite size scaling behavior. And in fact, we find it pretty well for the k-nearest neighbors approach. We get this this great sort of asymptotic convergence onto the correct finite size scaling behavior. The sort of rightmost points are quite small for this problem. They're 30 by 30. And then the leftmost point is a 140 by 140 lattice. On the other hand, the logistic regression seems to fail to do this. Instead, what we see is that it tends to estimate the critical temperature as being sort of exactly halfway between the training temperatures, with no real sort of scaling coming out. The error bars are calculated by a sort of comprehensive bootstrap, and they're what we use to try and reason that we are correctly obtaining the critical temperature, which we do using the k-nearest neighbors. We also extract the critical exponent of the correlation length via a curve collapse approach on our phase indicators, or the variance curve that comes from our phase indicators. And so for each phase transition, we do obtain an accurate determination of the critical temperature and the exponent of correlation length. The logistic regression approach, which we use because it had been used by some of these previous papers, we find fails in general to sort of latch onto it. As I mentioned, it sort of just tends to go from the midpoint of our training data. However, it does sort of provide a nice sort of side bonus. We can sort of look at pictures of the logistic regression coefficients to interpret what's important in our persistence images for distinguishing phases. So here's sort of what we get. And we see that, for the classical XY model or the BKT transitions, the low temperature phase is distinguished by the bars that are born very early. So the sort of spin waves in our models, and also this point up here, the bound vortex anti-vortex pairs. And the high temperature phase is distinguished by the change in behavior of these vortices and the sort of disorder indicated by bars appearing in this region. And similarly about what we said about domain walls in that transition. And so this work has all been summarized in our recent preprint. It went out in the archive at the end of last week. It has the same name as the title of this talk. But there's a whole load of work we want to do with this. So one of the main things we want to do is extend this to more complex models. So we really, the XY model was serving as a testing ground, as a sort of simple model where topological defects have an important role. But really, we want to be looking at lattice gauge theories. There's also work to be done in investigating what other topological data analysis machinery can tell us. So there's an idea called vineyards, which goes back to that stability property I mentioned earlier. So if a small change in the input data leads to a small change in the persistence, what happens if we track these small changes? And what we see is we can track the points in the persistence diagram as they form a path, which we call a vine, and then the collection of these vines forms a vineyard. So a small change in our input data might well come in when we do a Metropolis Hastings step. We make a small localized change to our configuration, and we can track the small change to our persistence. Maybe we can look at sort of the dynamics then of the Metropolis. And in fact, this would even provide a way to speed up these calculations on sufficiently high dimensional lattices. We could also look at representative cycles. So given a point in the persistence diagram, we can try and localize exactly which bit of the configuration it's talking about. And there's a whole sort of wealth of techniques and tools that are being actively developed in TDA. And then it seems sort of an obvious step would be to take this persistence image, this fixed size vector describing the topological defects in our configurations, as a sort of pre-processing step for an approach based on deep learning that could be used instead of or alongside the configurations. Thank you very much for your time. Happy to take any questions.
Thank you, Nick. Thanks for the nice talk. So questions. Let's start with the audience in Trento. Yeah, Srijit, I think you need to come here because I don't have a mic that works.
Hi, Nicholas. Thanks for the nice talk. Actually, I was intrigued by the first two slides where you drew the bar plots.
Yeah.
So
this or the
first where you started showing, yeah, exactly. How does the persistence diagram? How do you construct a bar plot in the first place? So this looks. I mean, in 2D it looks fine. So when you go for example, to a 3D XY model where the topological effects are more, I guess, you can, I mean, they're more abject. You can see, you can observe more complex topological phases in 3D XY model. So how do you think this bar plot is going to look like? The one that you showed, yeah.
Yeah, I see. So yeah, and that's sort of where the work comes in. Is the sort of the step where we have to do some thinking is in constructing this filtration. So there's a way of taking our data, our configuration, and producing this sequence of sort of geometric shapes.
I see.
And so what I've done is sort of built one that works for sort of 2D lattice spin models. But indeed, to extend this to other models, you need to come up with a new filtration.
But shouldn't, I mean, it also face the dimension, the curse of dimensionality, because in 2D, the shapes looks more easier to construct. For 3D, you get more.
Oh, yeah. The computational expense of computing this stuff does get pretty big with higher dimensions. Just constructing the filtration takes longer, and then computing this persistence sort of naive algorithm is sort of O(n) cubed, with n being the total number of sort of points in the complex.
Thanks.
I mean, if I can add a comment on the last thing, I mean, Nick used standard libraries, which are used in a variety of applications for these complexes. So it's a wider problem, especially these techniques are used in 3 dimensions in various contexts. And there are open source libraries which count those complexes. If I say something wrong, Nick, stop me and interject.
Well, Definitely the computation of the persistence is all sort of standard. You can find nice implementations. The construction of the filtrations sometimes you have to do that by hand.
Do we have other questions? I can't see any other questions. So we thank Nick and we close the session for today. I'll see you tomorrow.